two-stroke engine. If we observe the anatomy of these two engines, upon first glance they seem very similar. They both have a crankcase and a crankshaft together with a connecting rod. As well as a wrist pin and a piston. They also both have a cylinder and they both operate by converting the reciprocation of the piston into the rotation of the crankshaft, which then turns the gears of a transmission and ultimately the wheels of the vehicle. But beyond these core similarities, the four-stroke and the two-stroke start to fundamentally diverge, resulting in two very different approaches to internal combustion. And what I want to do today is give you the only video you need to watch to get a very solid understanding of how a four-stroke and a two-stroke engine work. We'll also be exploring the differences, benefits, and drawbacks of each engine type, and this will then answer the question of why the four-stroke ultimately prevailed over the two-stroke in most applications, despite being larger, heavier, more expensive, and more complex. So let's get started with the four-stroke. Why is it called a four-stroke? It's because the four-stroke engine needs four strokes to complete one combustion cycle. Every time the piston moves from top to bottom, or vice versa, that's one stroke. One stroke of the piston equals 180 degrees of crankshaft rotation. Now the four strokes are intake, compression, combustion, and exhaust. During the intake stroke, the piston travels from top to bottom, which are also known as top dead center and bottom dead center. As the piston does this, it creates an empty space or vacuum inside the cylinder. This newly created void is essentially a brief absence of air. And because we have an absence of air, we also have an absence of air pressure. In other words, we have a low air pressure inside the cylinder and atmospheric air pressure outside the cylinder. This air pressure difference cannot continue to exist, and air naturally seeks to equalize pressure everywhere. And so air, together with fuel from the outside, rushes into the cylinder and fills it with a fresh air-fuel mixture. By the time the piston reaches bottom dead center, all the air and fuel that can hope to get in have done so, and the piston now starts to move upward. As it does that, it forces the air-fuel mixture into an ever smaller space. In other words, it's compressing the air-fuel mixture, which is why this stroke is called the compression stroke. Just before the piston reaches top dead center, the spark plug fires and ignites the air-fuel mixture, which finds itself between the two electrodes of the plug. Although combustion inside an engine is often described as a bang or explosion, that isn't what's actually happening. An explosion is detonation, which is a rapid, uncontrolled process. In contrast to this, combustion is deflagration, which is a much slower, more even, and controlled process. Combustion spreads out evenly outward from the spark plug through heat transfer. The small portion of air-fuel mixture initially ignited by the spark plug heats up and ignites the next layer of the air-fuel mixture. This layer then ignites the next layer, and the process continues until all of the air-fuel mixture is burned. As the combustion flame front spreads, it rapidly raises the temperature and pressure inside the cylinder. Because the cylinder is sealed, this pressure has nowhere else to go, so it ends up pushing the piston down the cylinder with great strength. This is our combustion stroke, and of the four strokes, this is the only one that actually generates power, and it does so by converting the energy released by combustion into motion of the piston, which then turns the crankshaft and ultimately the wheels. By the time the piston reaches bottom dead center again, all the air-fuel mixture has been burned, and we now have exhaust gas, or the remains of combustion, inside the cylinder. As the piston moves up once again, the exhaust gases leave the cylinder and exit through the exhaust piping, catalytic converters, and mufflers out into the atmosphere. Now, if you know a bit about engines, then you've probably noticed how my explanation of the four-stroke combustion cycle fails to answer some very important questions. And these are: how do we allow air and fuel to get in during intake? How do we keep air and fuel as well as combustion energy from escaping during compression? and combustion. And how do we allow exhaust gases out? Well, the answer to all of this is the same thing, and it's valves. The intake valve opens during the intake stroke to allow air and fuel into the cylinder. Both valves are closed during the compression and the combustion stroke to prevent air and fuel as well as combustion energy from escaping the cylinder. And finally, the exhaust valve opens during the exhaust stroke to allow exhaust gases to escape the cylinder. Now the valves are operated by the camshaft, and as you can see, the camshaft has lobes on it. As the lobe contacts the rocker arm pushes onto the valve and opens it. As the lobe releases the rocker arm, the valve spring ensures that the valve returns to its seat as soon as possible. The shape of the lobe determines how much the valve opens and how long it remains open. The higher the lobe, the more the valve opens or the more lift we have. The broader the lobe, the longer the valve remains open and the more duration we have. But for the engine to run well, we must ensure that the motion of the camshaft is synchronized to the motion of the crankshaft and the piston. This is done by a cam belt or cam chain. It connects the crankshaft with the camshaft to ensure that the correct valve opens during the intake, that both remain closed during compression and combustion, and that the correct valve opens during exhaust. As you can see, our chain is very slack, and this is because our display model doesn't have chain guides and tensioners, which are normally present to ensure proper operation of the chain. As you can see, the four-stroke engine needs a lot of mechanical parts to get gases in and out of the cylinder. These parts are a source of weight and complexity, but also of friction, and they actually have to steal some of the engine's power to operate. As you can see, I need some strength to overcome the resistance of the valve spring and open the valve. This strength must come from somewhere when the engine is running, and so the valves actually steal a bit of the energy created by combustion to open themselves and allow the next combustion to happen. Additionally, all of these mechanical parts are a source of potential engine failure. If they aren't installed correctly and the timing of the engine isn't correct, it can result in the engine running poorly. In extreme examples, the timing can be so off that it results in the piston contacting the valve on an interference engine. An interference engine is one where the valves and the piston occupy the same space, but at different times. This can often enable a more compact, efficient, and powerful engine, but it also leads to engine failure in the event that the chain or belt snaps. Now, if we move over to the two-stroke, we can see that it replaces all of this with just this. In the case of the four-stroke, this is the cylinder head together with the valve cover, whereas in the two-stroke, we really have just a cylinder cover or cap. There are zero moving parts. No valves, no chains, no cams, no springs, and therefore less weight, less complexity, less cost, and less potential for failure. So then how does the two-stroke get gases in and out of the cylinder without valves? Well, if there's one thing you should take away from this video, it's this. The four-stroke only uses the area above the piston for the combustion cycle, whereas the two-stroke uses both the area above and below the piston. In other words, the intake charge or air and fuel mixture see both the area above and below the piston in a two-stroke, whereas the intake charge never gets below the piston in a four-stroke. Now let's observe the combustion cycle in a two-stroke, and we're starting with the combustion stroke itself and the piston atop dead center. So combustion has just started, it's building pressure in the cylinder and pushing the piston down, while at the same time we have fresh air-fuel mixture below the piston, and I'll explain how it got there in just a moment. Now as the piston is going down, it opens up the exhaust port, which allows some of the exhaust gas to start escaping from the cylinder, and at the same time, the downward motion of the piston is also compressing the air-fuel mixture below it and pushes it into the transfer port, which is still blocked off by the piston skirt. As the piston goes down some more, it starts to open up the transfer ports, which then allow the compressed air-fuel mixture from below the piston to be transferred above the piston. The pressure in the cylinder has already decreased substantially because much of the exhaust gas has been allowed to escape through the exhaust port. This means that the compressed air-fuel mixture coming out the transfer port is actually at a higher pressure than the remaining exhaust gases in the cylinder, which means that as the air-fuel mix enters the cylinder, it helps to push out the last of the remaining exhaust gases. But as you can see, our exhaust port is still open. It's not blocked off by the piston, which means that the air-fuel mixture not only pushes the remaining exhaust gas out the cylinder, the air-fuel mixture itself is also free to exit the cylinder through the exhaust port. This brings us to the first drawback of the two-stroke. The design of the engine means that some fresh, unburned fuel gets dumped out the exhaust. This, of course, is the definition of inefficiency, but there are ways around it, and we'll cover them in this video. So the piston is now at bottom dead center, and we have an air-fuel mixture above the piston as the piston starts going up. Now, in addition to pushing up and compressing the air-fuel mixture, the upward motion of the piston is also drawing more fresh air and fuel into the cylinder. As the piston rises from bottom to top, it creates a vacuum below the piston. Just like in the four-stroke, vacuum is the absence of air which cannot continue to exist, and so the air-fuel mixture rushes into the cylinder through the intake port and occupies the area below the piston. When the piston reaches top dead center again, we have compressed air and fuel above the piston, ready to be ignited, and fresh air and fuel below the piston, ready to be pushed into the cylinder when the piston descends again and opens up the transfer port. The two-stroke combustion cycle and design also explains why the two-stroke piston is much longer than the four-stroke piston. It must be long enough to keep both the transfer and the exhaust port blocked off as it travels and approaches top dead center. If the piston were shorter, exhaust gases could enter the area below the piston, but more importantly, the fresh intake charge could also escape out the exhaust port with the piston at top dead center. As you can see, each time the piston is at top dead center, a combustion event occurs. This also explains the name two-stroke. The engine only needs two piston strokes to complete its combustion cycle. In other words, each 360 degrees or one full engine revolution results in a combustion event. Whereas in a four-stroke engine, combustion occurs only every other time the piston reaches top dead center. Combustion occurs only every 720 degrees of engine rotation. This means that the two-stroke produces twice as many combustion events or power pulses for the same RPM, which means that, at least in theory, the two-stroke engine can make twice as much power for the same displacement compared to a four-stroke engine. The other important thing to note is that the strokes are very clearly defined and separated in a four-stroke engine. Each completed stroke of the piston marks the beginning of one and the end of another stroke of the combustion cycle. But the two-stroke engine sort of lumps the strokes together. They overlap and occur simultaneously. The two-stroke is actually multitasking, which enables it to squeeze more action into the same time frame. But as with everything, there is a price to be paid. My explanation of the two-stroke combustion cycle probably raised some questions, like, for example, what is this big gaping hole in the exhaust port, or how come the downward motion of the piston doesn't just push the air-fuel mixture back out through the intake? Well, no worries, we're going to answer these questions one by one, and their answers will shed light on the price that the two-stroke pays for its increased combustion frequency. Let's start with how we prevent air and fuel from going back out the intake when the piston goes down. To do that, many engines use this, and this is a reed valve, which is placed into the intake like so. A reed valve is essentially a one-way valve. It allows gases to enter, but it prevents them from exiting. When the piston moves up and creates a vacuum inside the crankcase, it also creates a low pressure zone inside the crankcase, while a high pressure zone remains outside in the atmosphere. This pressure difference forces the reed valve blades or pedals open. Vacuum inside the crankcase means that there's very little pressure acting behind the pedals, but there's atmospheric pressure acting on the other side of the pedals, forcing them open. When the air-fuel mixture enters the crankcase, the pressure soon equalizes. As the piston starts going down and compressing the air-fuel mixture, pressure actually becomes greater behind the pedals on the crankcase side, forcing them shut. The design of the reed valve is such that the pedals can only open in one direction, and so crankcase pressure closes the pedals and keeps the compressed air-fuel mixture from escaping back into the intake. Now, the elephant in the room that we have to address next is lubrication. If you have ever owned an engine in any kind of vehicle or appliance, then you probably know that lubrication is key for engines. Without the protective film of oil, metal-to-metal contact occurs and quickly leads to catastrophic failure. As you may know, in a four-stroke engine, everything under the rings of the piston is constantly lubricated by engine oil. This engine oil is also usually circulated, filtered, and pressurized by an oil pump to ensure that the film of oil between metal surfaces is always strong enough to resist all the forces which are trying to break it apart. So the elephant in the room is the area under the piston inside a two-stroke engine. If this area constantly sees air and fuel, then how do we keep it lubricated? Obviously, getting the same quantity of oil here as in a four-stroke and keeping it circulated is impossible. It would end up in the combustion chamber and probably prevent combustion from ever occurring. We also know that fuel is a solvent, making things even more difficult for the rotating assembly of the two-stroke. So then, how do we prevent metal-to-metal contact in the two-stroke? Well, the answer is a compromise. Instead of only getting air and fuel under the piston, we get air, fuel, and oil in there, but we keep the quantity of oil low enough to prevent it from impeding combustion, but high enough to provide some lubrication to the moving parts of the engine. There are two possible ways to get the lubricating oil or two-stroke oil into the engine. The older method is to pre-mix the oil with the fuel that goes into the fuel tank. The second, more modern method is to have a separate tank for the two-stroke oil and have an injection pump which injects the oil into the engine, usually into the carburetor where it mixes with the fuel and air and ends up inside the engine. Now, the ratio of air to fuel inside the engine is usually somewhere around 13:1, and the ratio of two-stroke oil to fuel is anywhere from 24:1 to 50:1. This gives you an idea of just how minimal the amount of lubricating oil is inside the engine at any one time. Because it's mixed together with the air and fuel, the oil also inevitably ends up inside the combustion chamber where it gets burned. This is where the smoke and the smell of two-stroke engines comes from. Two-strokes essentially burn small amounts of oil all the time. This is also why the lubrication system of two-stroke engines is known as a total loss lubrication system. The oil never gets replaced like in a four-stroke. Instead, it's lost and topped up as necessary. This means that the lubrication of the rotating assembly of a two-stroke isn't nearly as consistent or reliable as in a four-stroke engine, which ultimately leads to a significantly shorter maximum potential lifespan for a two-stroke. No amount of maintenance or lubrication quality can overcome this inherent design constraint, and the average lifespan of a two-stroke engine on a motorcycle is somewhere around 15 to 20,000 kilometers. Some may do more than that, but many won't make it even that far and will need their pistons replaced and bottom ends rebuilt well before that. Racing two-stroke motorcycles often need rebuilds after only 15 to 20 hours of operation. In contrast to this, four-stroke engines on motorcycles, even small ones, can make it to 50,000 kilometers. Some even get to 100,000 kilometers and beyond, whereas engines on cars and trucks regularly make it past 300,000 kilometers. Some even get up to 1,000,000. The flip side of this is that although two-stroke engines require more frequent rebuilds, their rebuilds are usually much less expensive and far easier to perform. The other problem with a total loss lubrication system is that burning oil is obviously very bad for emissions, which is the key reason why many legislations around the world have outlawed the manufacture of street-legal two-stroke vehicles and only allow off-road and competition two-stroke vehicles to be made and sold. The difference in lubrication systems between the two engines is also embodied and evident in the piston rings. The four-stroke has 3 rings, whereas the two-stroke only 2. The third set of rings in a four-stroke are oil control rings, and they prevent oil from getting into the combustion chamber. Oil control rings are obviously unnecessary in a two-stroke because the oil gets into the combustion chamber anyway, with or without them. But there's a benefit for the two-stroke here because less rings means less friction and less power losses due to this friction. But the piston rings don't just differ in number. They're free-floating or allowed to rotate in the four-stroke, whereas in the two-stroke they are pinned in place using small pegs. Now these pegs are missing from this particular piston, but you can still see the holes where the little pegs or locating pins go. Their purpose is to prevent two-stroke piston rings from rotating. This is done to prevent the piston ring ends or gaps from snagging onto the exhaust or the transfer ports, which would lead to engine failure. Instead, the rings are fixed to ensure that the gaps always travel over the area between the transfer ports to eliminate the possibility of getting snagged by the ports. The free-floating ring system of the four-stroke is actually superior because allowing the rings to rotate can help ensure more even wear of the rings and a longer-lasting engine. The lack of consistent lubrication is also why two-stroke engines often use ball bearings and or roller bearings as their rod and crank bearings. Ball bearings are more expensive and require more space than plain bearings, but they're far more resilient to poor lubrication environments. On the other hand, most four-strokes can use plain bearings which are very small and inexpensive and which together with a good film of oil offer excellent load bearing capacity and higher shock resistance.
With Shopify, I can turn my passion for coffee into a business. And that sound, when somebody buys something, it's a little addicting. Come on, you just want to hear another one? Start your free trial at shopify.com.
But our example four-stroke engine actually uses ball bearings too. The reason is that this is a very compact and inexpensive engine which has a very small oil pump that isn't able to provide the kind of lubrication that oil pumps on the larger, more advanced four-strokes can. Another area where two-strokes are limited is the compression ratio. The compression ratio of the engine is the ratio between the largest and the smallest volume of the cylinder, or the ratio between cylinder volumes when the piston is at bottom and top dead center. The higher this ratio, the more we compress the air-fuel mixture, leading to the air and fuel molecules being packed closer together, which then improves combustion speed and strength, leading to higher efficiency and power. Now, both of our demonstration engines are actually single-cylinder 125cc motorcycle engines. Our four-stroke is from a 90s Honda Spacey scooter. It makes 10 horsepower and 10 newton meters of torque and has a bore of 52.4 millimeter and a stroke of 57.8 millimeter. Our two-stroke engine is from a Yamaha TZR Belgarda sports bike, which is also from the 90s. It makes an impressive 28 horsepower and a less impressive 16 newton meters of torque and has a bore of 56.4 and a stroke of 50 millimeters. One of the reasons why the four-stroke engine looks very underpowered is because space constraints in a scooter lead to restrictive intake and exhaust designs. The other reason is that the scooter engine is focused on economy and user-friendly power, whereas the sport bike engine is focused on building peak power, which it manages to build and hold over only a very narrow part of the top of the power band. Although both engines have similar bore and stroke specs, they have very different compression ratios. The four-stroke engine has a compression ratio of 9.5 to 1, whereas the two-stroke engine manages only 5.9 to 1. Why is this the case? Well, the reason is very simple, and it's because the four-stroke utilizes the entire volume of the cylinder. Compression begins when the piston is at bottom dead center and ends when the piston reaches top dead center. Things are different in the two-stroke. Compression does not begin at bottom dead center. Instead, it only begins when the piston closes off the exhaust port. Before the exhaust port is closed off, the cylinder isn't sealed, and air and fuel can't be compressed. Instead, they're free to escape through the exhaust port. This is why in a two-stroke, the compression ratio, or the ratio between the largest and the smallest cylinder volume, is the ratio between this and this volume. Obviously, this is much smaller than this and leads to a much lower compression ratio, which ultimately limits efficiency and performance in a two-stroke engine. The final difference is that the four-stroke is inherently more flexible thanks to its more complex, bulkier design. And the key factor behind this lies in the camshaft. A camshaft is essentially the mechanical brain of the engine, and changing the camshaft can completely transform the character and performance of the engine. But you don't even need to change the camshaft. You can simply shift its angle in relation to the piston, which is known as advancing or retarding the camshaft to impact engine power and torque. And this can be done while the engine is still running. Most modern engines on cars incorporate variable valve timing systems which advance and retard camshafts as required to produce good responsiveness and torque at low RPM and good power at high RPM. Many systems even pack multiple lobe profiles into a single camshaft and can switch between them during engine operation, giving us a low valve lift at low RPM and high valve lift at high RPM, which further improves responsiveness, power, and torque throughout the rev range. In contrast to this, the two-stroke cannot change the position of its ports. They are a fixed part of the engine's construction. But what a two-stroke can do is change the size of the exhaust port. And this finally brings us to the big round hole in the exhaust port. It's meant to house this. And this is a part of a system called YPVS, which stands for Yamaha Power Valve System. Other manufacturers also develop their own systems with their own acronyms, but all of these systems have the same goal. And despite what their name is saying, the goal isn't to increase power. Instead, the goal is to even out the power band of a two-stroke, resulting in a smoother, more usable, and more linear power band and power delivery. Our particular example is what's known as a guillotine-style power valve, and it rotates to make the exhaust port smaller at low RPM and larger at high RPM. Now, the power valve works together with another signature feature of two-stroke engines, and that is the expansion chamber present in the exhaust. Now, the expansion chamber relies on the principle of wave resonance, which is similar to what you experience when your voice creates an echo. When the initial acoustic wave of your voice encounters an obstacle, it gets reflected back as a delayed, weaker acoustic wave. The exhaust pulse coming out from the engine is also essentially a wavefront, and when it encounters the changing diameter created by the expansion chamber, it reflects another wavefront back to the cylinder. This wavefront can then be timed to push back the fresh air-fuel mixture that's trying to escape through the exhaust port. Now, at low RPM, the piston is moving slowly, and this means that the reflected wave from the expansion chamber can easily make it in time to push the fresh air-fuel mixture back into the cylinder. This is why we don't need the entirety of the exhaust port and can reduce its size. The benefit of the reduced exhaust port size is that during combustion, we keep the cylinder sealed away longer, which means that we can harness more of the combustion's energy, which results in better responsiveness and torque at low RPM. As RPM increase, the piston moves faster and faster, and so there's less and less time for the reflected wave from the expansion chamber to make it back to the cylinder and push the air and fuel back in. So we increase the size of the exhaust port to buy more room and time for the reflected wave to do its thing. We do sacrifice the increased duration of cylinder sealing, but we're already at high RPM, so building power and torque really isn't an issue at this point. So it seems that a reduced lifespan together with high emissions and poor efficiency spelled doom for the two-stroke. Well, there's a glimmer of hope in the future of two-strokes, and it comes in the form of direct injection. Direct injection basically means that we're spraying fuel directly into the combustion chamber via an injector, instead of bringing it in from the intake port via a carburetor. Direct injection also has benefits for four-stroke engines, and many modern four-stroke engines in cars feature direct injection. But the benefits of direct injection are more significant in the case of two-strokes. By spraying fuel directly into the chamber, we can start introducing the fuel only when the exhaust port gets closed off by the piston and compression actually begins. This prevents fresh fuel from being dumped out the exhaust port, which obviously dramatically improves efficiency and emissions. It also removes the solvent properties of fuel from under the piston, which can help improve the lubrication of the rotating assembly. However, there are some challenges to implementing this technology, and it's still in the development stage, and only time will tell if and when it will become a mass production reality.